Welcome back to Comp 1405. In this chapter, we're going to talk about algorithm complexity featuring searching and sorting. Now that we've built some programs, we've seen that there's a lot of different ways that we can solve any given problem. And you probably noticed that some of those solutions are better than others. For example, we could print all the numbers from 1 to 1,000 by writing a for loop with a print statement, or a while loop, or we could just use 1,000 individual hard-coded print statements. So in this chapter, we're going to learn about comparing algorithms in terms of their efficiency. We're going to demonstrate this by learning about some searching and sorting algorithms. Searching and sorting are important problems in computer science. This is because programs use search pretty much any time you want to find a piece of information. So user login, or finding a song on your phone, or doing a Google search, or pathfinding in video games. So it's important that our searches be fast, and we can improve the speed of our searches by keeping our data sorted. So searching and sorting are important problems in computer science. When designing an algorithm to solve a problem, how do we know that we've designed a good algorithm or not? So two measures of a good algorithm are correctness and efficiency. The correctness is, does this algorithm do the thing it was supposed to do? Does it solve the problem we asked it to? And efficiency is, does it do that quickly? Does it use minimal resources while attempting to accomplish this? We can measure the correctness of our code by testing it, but how do we measure efficiency? What about clock time? We could just run our program and see how many minutes or seconds it takes for our program to run. While that would be one way to measure the efficiency, right? If we have a program that takes 3 days, that's a lot slower than a program that takes 3 seconds. So this will work to distinguish very different algorithms, but once we're trying to compare very similar algorithms, there's a problem in comparing them because this measure is quite inconsistent. Right? In order to measure how long it takes for a program to run depends on how fast the CPU will be. So if we have different machines, we'll get different speeds. And then even on a single machine, we'll have variations in speed from one run to the next, depending on the environment of that machine as it's executing. Another downside of using clock time to measure our algorithms is that it requires us to actually code and execute the algorithm before we can measure it. So in order to measure efficiency, it helps to consider the opposite of efficiency, and that's complexity. How much work does a given algorithm need to do in order to complete its task? So if we have something that's more complex, then it's going to be less efficient to solve. It should be noted there's also the concept of space efficiency, which is how much memory does our algorithm require in order to solve the problem, not just the time, but the amount of space. But we'll leave this concept for your future courses. For now, we'll just consider time complexity. So to measure the complexity of an algorithm, we have to count the basic operations that that algorithm does. So basic operations are these simple operations that we consider to have a fixed computational time. For example, things like a comparison, or a single arithmetic operation, or a single assignment operation. In theory, these are things that we can consider to take single instruction cycles on our computer. It's good practice to state which operations you're going to use as these unit costs in whatever analysis you're doing. But once we have this unit operation or these unit costs established, complexity is then a count of those unit costs done by our algorithm. So the number of comparisons or the number of arithmetic operations that happen in our algorithm. Consider, for example, searching a list. Searching is the act of going through a list of items looking for a specific one. So the inputs to this problem is a list of items and some key or target item we're looking for, and the output would be true or false if it's there or not, or possibly the index of that key item within our list. So the question is, how many items will we need to compare in order to find the key in the list? It's important to note this depends on the length of the list as well. Right? If we have one item in that list, it's very easy to determine if our target is in that list. Single comparison will tell us yes or no, is that the item? If we have 1,000 items in the list, well then it's going to take a lot longer to determine whether or not our item's there. So complexity is a measure of the fundamental operations, or these unit operations, relative to the size of the problem. Let's look at a more specific example. So the linear search algorithm, also known as sequential search, is the most basic brute force search algorithm you can find. So the idea is, given some list, we're looking for some target, and the steps are we'll just start at the front of that list, so item 0, and we'll ask each item, are you the one we're looking for, yes or no? So we'll step through every item in the list until we find the one we're looking for. Once we found it, we can return the index where we found it, or we can just return a Boolean whether or not it was found. Linear search is one of those algorithms that shows up in real life a lot. As an example, if you wanted to find a specific game on this shelf, there's no particular order to it, so you just have to search the entire shelf to see if the game you're looking for is there. Another example would be finding the ace of spades in a shuffled deck of cards. You just have to go through every card until you find the one that you're looking for. As another important example is if you wanted to find the very best fruit from this basket, for example, the largest fruit from this basket. If you wanted to be sure that you had the very largest fruit, there's no way to do this other than checking every single fruit and determining which one is the largest. As another example, imagine it's 1993 and someone keeps calling you and not leaving messages on your answering tape machine. So you have their number, but you want their name. Now, in order to find them, you have this book that has a list of everyone's name and number. Of course, it's sorted by name, so having their number doesn't help. You just have to go through and check every single number one by one until you get their name. Returning back to the realm of computer science, imagine we have a list of numbers. In order to do a linear search, all we do is we start at the beginning and we search through each one. So for example, if we're looking for item 14, we start at the first one and say, is this 14? It's not, so we go to the next one, the next one, the next one. Eventually we land on an item that happens to be the number we're looking for, so we can say either true or return index 4. Now in this case, we had to make 5 comparisons to get there, because we had to check the first, second, third, fourth, and the item that we found. So linear search is just the literal embodiment of straightforward. We're checking each item, comparing it to our target, and then stopping when we found it. Returning to VS Code with a different voice. Let's see how we can create a linear search algorithm in Python. So in the provided code, there's a shell of a main function here that defines 2 lists called names and ages. And this is written so that the names and the ages both have the same number of items, and the names and ages match up. So the age at 0 is the age of the person at names at 0. So in this case, Kelly is 29, Ray is 47, Quinn is 84, Isabel is 35, etc. So we have an assertion here that just says make sure that that's true, that these 2 things have the same length. And now we can use this information to just do some searching. So now let's create a linear search algorithm that can answer the question, is Frodo in this group of people? So in our main, we can say something like, is Frodo in the group? And to answer that, we would just do a linear search. So we'd say, is Frodo equals linear search through the list of names for the name Frodo. And then if that's true, we can say print, let's do an F string here, Frodo is in the group, and then true or false, depending on what we get. So this assumes we have a function called linear search, so let's define that linear search function. So a linear search function takes in a given list and a key that we're looking for. So in this case, our list is the list of all names, and the key we're looking for is one specific name that may or may not be in that list. So we can say this function searches a given list for a given key and returns true if it is found. So to implement a linear search is really quite straightforward. We're just doing a traversal through each element in the list and checking with each element, is this the one we're looking for? Is this the key? If so, we're done. If not, we continue. So we just say for each element in our list, is this the element we're looking for? If element equals key, then we found it, so we can return true and we're done. Otherwise, we keep looking, we keep looking, we keep looking. If we get to the end of that list and we don't find it, then it's not there, so we return false. Let's save our code and try it out. So we say python linear search.py. Nothing happens because we didn't actually execute main. Remember to call our functions. And when we run it, we get Frodo is in the group true. So it did a linear search through each item in the list, and it found the item that was there. Notice that a linear search works a lot like the in operator. So if, for example, I replaced this line here where we called linear search with just is Frodo equals the string Frodo in our list of names, we get the same result. And while this seems like it's doing less work because it's in a single line rather than calling a whole function, the in operator is deceptively simple. It's only 2 little characters, but it actually means to do all that same work. So the in operator does actually run a linear search through the list of all of our items, in this case names, for the key that we're passing in. So while this looks like it's less work just because it's simpler to type, the actual work, the complexity of this operation is the same in either case. But let's put that back so that we're using the stuff that we're learning today. Notice also in the definition of our linear search, the return false is outside of the loop. What would happen if, for example, I were to say else return false like this? Would this do the same operation? Would this complete the same linear search that was asked? Well, let's save it and find out. When we run our code, we get false. So our code works, it doesn't crash, but it doesn't give us the answer that we're expecting because obviously Frodo is in this list somewhere here. So the issue here, if we walk through the steps of this loop, our for loop takes the first element from our list and checks, is that the item we're looking for? If it is, we return true. If it's not, then we return false. If we have a branch here that's always going to return, in both cases, we're going to exit the function, which is to say, this loop isn't going to do anything. It's going to check a single element and then do no repetition. So just a simple error to be aware of. We can stop early if we find the item, but if we don't find the item, we have to continue checking until we reach the end of our loop. So this return false needs to be outside of the loop. Next up, what if we wanted to answer the question, how old is Gandalf? Could we solve this using a linear search? Well, the idea here is we need to be able to find the name so we can get the index of that name so that we can use that index to get the age from the other list. So we can't use our current linear search because that'll just tell us true or false is Gandalf in the group, whereas we need to know where in the group Gandalf is. So in this case, I'd say Gandalf's index equals to some linear search that returns an index. So I'll say linear search index, a new function we haven't yet written. And we'll search through the list of names for the name Gandalf. Now if we find it, then Gandalf index here will have the location of that item in our list. So what we need to do then is use that location to print out the age. So we could say print Gandalf is, and then using the ages list, so we'll say ages at Gandalf index years old. So now in order to run this search, we're going to have to create the linear search index function. So let's make a new linear search. Given some list and some key. And this will do the same thing. It's going to search through each item, traversing the list to find if that key is in that list. But now if we find it, we want to return the value. So we'll say searches a given list for a given key and returns the index if found. So now instead of using a for each loop, we'll have to use a regular for loop. So we still know at maximum we're going to search every item in the list. So we can use a for loop going from 0 to the end of our list and just check each item again. So we'll say for I in range from 0 to the end of our list. And now at each one of those indices, we want to check, is this the item we're looking for? So if list at I is equal to the key that we're searching for, and in that case, instead of just returning true, we'll return the index itself. So return I. Now, if that wasn't the item, we'll go on to the next item, the next item, the next item, until eventually we'll be out of items. If the item that we're looking for isn't in the list, then we'll just return -1. Why -1? Well, -1's like false. It's a signifier that we didn't find the item we're looking for. And -1 itself isn't an index in our list. Right? Our indices go from 0 up to the length of the list -1. So negative indices are out of bounds. So this acts as a signal that's still of integer type, but can tell the user or the calling program whether or not there was a success. All right, so how old is Gandalf? Let's make sure our function has a different name. So we'll call this linear search index and save and run our code. And now it says Gandalf is 2,000 years old. So skimming through this list, that's the only one that's that size of value, so that kind of makes sense. We can one-to-one verify by hand that that's the correct number, but this is the number we're expecting. Gandalf in his human form, that is. Gandalf in his spirit form, many, many tens of thousands of years older, if we're getting specific. So that seems to work, but what happens if we asked to do a linear search for someone that doesn't exist? So if I had said, for example, how old is Zorro? We can walk through similar steps. So I can say Zorro index is equal to linear search index through the list of names for the name Zorro. Now, thinking through what would happen if the search fails, Zoro index would be a -1. And if we do a similar step to what we did with Gandalf and just assume that it worked and print out ages at -1, that's going to return the very last item in our list, which isn't necessarily Zoro. If I scroll the screen over, the last name is Ellen, so that wouldn't line up. That would be a logic error. So what we need to do is, once we've done our linear search, is verify the result. So we can say if Zoro index does not equal -1, that means we found the actual location, so it is in the list. We can print Zoro is, and do the same thing as before, ages at Zoro index years old. And in the case where it wasn't found, we can say else Zoro not found. Try it out. We run our code, and it says Zoro not found. So when we're doing a linear search for the index of an item, we should check to make sure the result of that index search gave us an actual index before attempting to use it. If it gives us back a -1, that's a signifier that our search didn't work, and we shouldn't assume that that value can then be used as an index. Next up, let's consider a special case of the linear search. And that's the job of finding the smallest item in a list, or the largest, or the best, or the mostest, whatever superlative you're trying to find. You're trying to find the ultimate item from the list out of all of the other items. So, without loss of generality, let's consider the problem of finding the smallest item in our list. So we have a list of, let's say, ages. We want to find the youngest person in the list. This is a special case of the linear search because it requires that we check every single item. We can't do early stopping once we've found the correct item because we don't know what the correct item is. We're doing a linear search through a list, but we don't have a key that we're searching for. We don't know the age that we're looking for. We want to find the smallest age. So we can't check each value in the list against the key that we're passing in because we don't have a key. Which means we can't know if we found the item that we're looking for until we've seen every other item. The pseudocode for this linear search is the same as it normally is. It involves a traversal through each item. At each item, we'll check to see if this is the item we're looking for. But the item we're looking for here is no longer does it match our target, but is it smaller than the smallest item we found so far. So that is, we'll start with some item. We'll say the very first item. That's the first item we've considered. Then it's the smallest item we've seen. And then we'll check the second item. We'll say if that's smaller, that's our new smallest so far. We'll check the third item. If that's bigger, we'll discard it. Check the fourth item. If that's smaller, then that becomes the smallest so far, and so on. Once we've checked all of the items in this way, the smallest so far will be the smallest overall. And that's the item we can return. Returning to our VS Code demo, we can say something like, who is the youngest person in our list? And to answer that, we'll say youngest index equals find smallest, a function we haven't yet written that takes in all of the ages and returns the index of the smallest one. Once we have that, we can then use that index to print our answer. So we can say print f the youngest person is, and we'll use the names list to get their name, but since they're aligned, we can use the same index. So youngest index at age, and then we'll say their age as well. Ages at youngest index. So the youngest person is their name at age, and then their age. So now all we need to do is create this find smallest function. So let's do that as well. So we'll say def find smallest. Now notice in terms of parameters, we only have one value being passed in as an argument, so we only need one variable up here as our parameter. In this case, just the list that we're searching through. So I'll say list. And now in our function, we're going to traverse through all the items, checking to see if the current item is smaller than our smallest so far. So before we can do that, we need to have some initial value for that smallest so far. So I'll call this the index of smallest. This is the smallest so far. And we'll say that initially is 0. So initially, the smallest item is the first one. Okay. And now in our search, we have to traverse all of the items, but we don't need to start with that first one because we've already assumed that's the smallest of the one that we've considered. So our traversal now can start with the second item and say, is that smaller than the first one? And then continue on from there. So we can say for I in range from 1 up until the end of our list, so len of lists. And now for each item that we're considering in this way, we say, is this smaller than the current smallest item? So if the current item is less than the smallest so far, so that's list at the index of our smallest so far, so index of smallest. So if the item we're looking at is smaller than the smallest one we found so far, then the item we're looking at is the new smallest so far. So we'll say the index of smallest moves to the current location. And what that means is once we're done this loop, we've gone through and we've done this for every single item, then that pointer, that index of smallest, will point to the smallest overall. Right? If it was that very first item, if the smallest item in our input list was at index 0, then throughout this loop, that if statement will just be false, false, false over and over and over again, and index of smallest will still be 0. If there was a smaller item in that list, we would have updated it, and now index of smallest would point to that instead. So when we're done, we can just return index of smallest. So again, note in our inputs, we have just the list. We have no key that we're actually searching for because we don't know what the smallest item is. So initially we say the smallest is the first item. We look through all of the other items, and for each one we say, is this smaller? And if so, then we keep track of that. And when we're done, the smallest so far points to the smallest overall. Now this is a linear search, but it's a linear search where we can't stop early. So in our previous linear searches, when we found the key that we're looking for, we can return true. In the best case, if the key's right at the front of our list, we only have to do one comparison. We check that first item, that's the item we're looking for, and we're done. We only had to do one comparison. In the worst case, either it's the very last item or it's not there at all. We have to check every single item before we can either return true or eventually return false. On average, if our item is in the list and the list is randomly sorted, we can expect to have to check half of those items. So if we have n items, we would expect n over 2 comparisons. When we're looking for the smallest or the biggest or the mostest, whatever, there is no early stopping, so the best case is equal to the worst case is equal to the average case. We have to check all of the items every time. Let's save our work and try it out. Scroll down so we can see, and run our code. And it says the youngest person is Leo at age 12. So just skimming this list, we can see the smallest number to a human is pretty easy to see is 12, and then we can line up the names to see that that matches Leo. What if we wanted to check if all of the elements in our list fit some criteria? So for example, what if we wanted to know, is everyone an adult? So is every person in this group 18 or older, let's say? So we can solve this with a linear search as well. The idea being, we still traverse through our items. We don't have a key here that we're looking for, but we do have a criteria. And in this case, we want to make sure that everyone matches our criteria. Which is to say, if we get through this list, checking every single person, and none of them failed our criteria, then we know that everyone matches that criteria. But as soon as we find one person who's not an adult in this case, then we know the answer to this question is no, so we can stop searching. Since it's just a Boolean question, yes or no, in this case, as soon as we know the answer is no, we can stop. But for each person in that list, if they match the criteria, then we still have to keep searching because the next person in the list might not. So we could say something like, is adult equals all adults, given the list ages. And then we can print everyone in the group is an adult, colon, and then we'll just true or false, whatever we got from our function. Okay, so let's create this function as well. So we'll say def is adult, given some list, we'll call this the age list. And now we'll search through this. This searches an input list of numbers and returns true if all numbers are at least 18. So the code for this, again, relatively straightforward. All linear searches are pretty easy to code. They're just traversals. So I'll say for x in age list, and now if x is an item from this list, I want to know, is this item greater than or equal to 18? And if it is, that doesn't tell me anything about everyone else, so I have to keep searching. If it isn't, that means I can stop. So the question is the reverse of what I'm really looking for here. Instead of checking to see if x is greater than or equal to 18 and continuing to do nothing, I should check, is it less than 18, in which case I can act. So I say if x is less than 18, then we'll return false. If not, then we do nothing. We go on to the next item, the next item, the next item. If we went through all of the items in our list and we never returned false, That means everyone in our list is greater than or equal to 18, so we can return true. Is adults. This was called all adults, not is adults. Okay, save our code. Is adult, is adult. Was it pretending I didn't do anything? Oh, I forgot the F. There we go. Clean up our code a little and run our code. So we'll say linear search. Everyone in the group is an adult, and it says false. It doesn't tell us who failed that criteria. We can modify our code to return the index instead of just true or false. But the idea here being, if we scan down our list with our eyes, we can see someone's 12, so right away the case is false. So it would do 1, 2, 3, 4, 5 comparisons in order to return false in this case. Now, if that wasn't there, it would have to keep searching until it found the next one that wasn't 18. If that wasn't there, it would have to keep searching, keep searching, keep searching, and get all the way to the end before it knows that everyone in the list matches our criteria. So the linear search is pretty straightforward to code, but there's a bit to consider about it. So in terms of correctness, the linear search will always work. It will find the data if it's there. Right? If we just have a list of information, we can check each item in that list and return true once we found the item we're looking for. In order to use a linear search, our data doesn't have to be sorted or stored in any particular order. We can just check every single item. It doesn't matter. We'll see later that sorting our data actually makes searching faster, but if our data is unsorted, a linear search is the way to go. We just brute force check every single value. So in terms of correctness, linear search will solve our problem and is generally easy to implement. But in terms of efficiency, linear search is not super efficient because it has to look through every single item in turn. As I said, the worst case is that the item is at the end of our list. We have to do n total comparisons. So if we have 100 items, we'll have to do 100 comparisons. If we have 1,000,000 items, we'll have to do 1,000,000 comparisons. The best case is that the item is at the front of our list, in which case if we have 100 items, we only have to do one comparison. We have 1,000,000 items, but the item's still at the front of that list, we still only have to do one comparison. On average, if the item is there, we expect to do n over 2 comparisons. But in general, since we don't know if it's going to be the best or the worst case, we say that the linear search will do at most n comparisons to search a list of length n. Notice it's never worse than having to search every single item. Right? If we have 1,000,000 items, we're not going to have to do 2,000,000 comparisons. We're not going to have to check every single item twice. We just check every single item once. So the worst case runtime of this is all of the items.